Yeah, thanks. So we're going to finish out the USHAG problem today. We're doing a reacting system now. So you can do the internal entropy all the way through the Gibbs energy for anything. You can do it for reactants, you can do it for products, and then once you have both sides, then obviously you can do deltas and see how things change. So we're going to do the USHAG for the products today, and then we're going to do the deltas, and then we're going to talk about the equilibrium constant. So we have this reacting system. Now, I caught an error in the notes. It's correct on this page, but as you go further down, it changes up here. And can you hit that middle switch? On the bank of 5, just hit that middle switch. That's washed out. You'll see like 4 or 5 panels in or slides in, this text is different. And I just didn't find it. I didn't copy and paste over it yet. So I did that this morning for the notes. So whenever you see it talks about 100 wave numbers and 200 wave numbers in the incorrect text on your notes, just scratch through that. We're still doing the same problem, that we start with right here. So this is the text for the whole problem today up at the top. So what we're doing is we're saying if this is the reactants, what happens if the products are the same energy levels but with degeneracy? Now let's see if we can just test your chemical intuition. If I throw molecules at this, and there's this dividing line between molecules in this system would be called reactants, and molecules in this system would be called products. Okay, so we throw molecules in there. Statistically, they can go anywhere they want, but they're going to fall down because of the Boltzmann's distribution. So there'll be more, preference for the ground state. So you'll have this thermal equilibrium, but which side of this reacting system do you think will be prevalent? Which side will have more molecules? I just want to test your chemical intuition, and so I would say raise your hand on the count of 3 if you think the products would have more molecules in it than the reactants. So 1, 2, 3, just one. What about the reactants? Everybody else thinks the reactants would have, or do y'all want to vote again? And try again. So raise your hand if you think the products are going to have more molecules in it than the reactants at equilibrium. You can take time to look at it. Naturally, if we dump all of our molecules into the reactant side, it's not at equilibrium, right? So it's going to distribute. And if we dumped all our molecules in the product side, it's not at equilibrium, it's going to distribute. So we're talking about after that distribution, which side has more molecules in it? How many say products? A few more people? Okay, y'all are saying reactants? Okay, so great. That's our chemical intuition. Let's see what the numbers tell us. Okay, so this is just a recap of the reactants. RCT I'm using for reactant. Okay, so these should be the numbers that we got last time. 87.9 wave numbers for the internal energy. 0.5 wave numbers for every degree Kelvin is our entropy term. Then the enthalpy, 295. The Helmoltz energy, negative 87. And the Gibbs energy, 120 wave numbers. So those are our reactant USHAG values. Okay, let's calculate the product. So here's the product partition function. It's the same. Oh yeah, there's another copy and paste error. Gosh, I'm sorry. I change these from year to year, and then I'll change the text, but this should be 200 and 400. Okay. It's so hard to find all the little places where things need to be changed. So that's 200 and 400. So that's the same as what we had before, but the only difference is the degeneracies, right? So, for the 200, it's going to be e to the minus 1, and for the 400, it's going to be e to the minus 2, but it's going to be times 2 for the first excited state and times 3 for the second excited state. So we get 1 for the ground state for that Boltzmann factor, 0.761, because remember before it was like 36. 37 or something like that. And so we've doubled it. So the e to the minus 1 was, 0.3 something, and this is 0.7 something because we had to multiply by 2. And then the Boltzmann factor for the most excited state, that second excited state, was going to be, it's like I don't remember what it was, 14 or something, and then we multiplied by 3. So it's up to 0.435. So these are the various Boltzmann factors for the ground and excited states in the product side. So we sum those together, and that's the partition function. So we get 2.196 for our partition function here. Okay, for the probabilities, it's each one of those numbers divided by the partition function. So we have 20% probability in the top, 35% in the first excited state, and then 46% in the ground state.
But the numbers are still all the same?
Yeah, in the rest of the table, I did it with the 200 and 400. Yeah. So this was just like a typo. Oh, okay. Yeah. So I didn't use the 100. I used the 200. So I do it in a spreadsheet, and so I know that all the formulas are there and everything. And I'll pull the spreadsheet up later if there's time. You can see, because what we can do is then we can change the temperature and everything, shifts around. Okay. So then we do the energy, the expectation value. So 400 times the 20, and then the 200 times the 35, and then 0 times the 46, and we sum up those energy components, and this is the total energy, the internal energy for the products, 148 wave numbers. Okay. So we could do a delta U. We'll do it at the end, but let's calculate USHAG, all of them. So let's do the entropy next. Okay. So now we have the values here, all the different equations for entropy and Helmoltz energy and all of that. So here's the entropy equation. So 148 was our energy. We divide by the temperature and then multiply by R ln Q. And remember, if we're in wave numbers, we do that K over HC. And so we end up with an entropy of 1.045 wave numbers per degree Kelvin. Next, we can do the enthalpy, 148 plus RT. So again, R in all of these systems, whenever you have wave numbers, is going to be that 0.695. Don't use the 8.314 because your units won't work out. Then we have the Helmholtz energy. So that would be U minus TS. So we have the entropy here. So that's going to be negative 163 wave numbers. Once again, our absolute value, or not our absolute value, but the magnitude of our Helmholtz energy is coming in at negative for these systems. But the Gibbs energy uses the enthalpy. So you got to do the enthalpy first, and then bring that 356 down. H minus TS. So we have the entropy here, and this is our Gibbs energy, 44 wave numbers. So that's USHAG for the full set of products. Any questions on this? This should be pretty easy. Once you have the equations here, the real trick is just getting the table done with the partition function. Yes?
How many exams are you going to give us the equations like you did last year?
Yeah, so it's going to be, so it's, let me think about that. You get a note card in this class too. Okay, yeah. So these calculations are pretty long, so I don't know that you'll finish the test, right? If I were to just say, here's this reacting system, tell me the equilibrium constant, right? But I will produce like a whole diagram that has out of Excel, and I'll show you the Excel sheet. It has the reactants on the reactant side, the products over here. You have USHAG, all of the calculations, and there'll be some missing cells.
Okay.
And so you just need to know the problem forwards and backwards. You're like, okay, I got to calculate the partition function. I know what to do here. Over here, I got to calculate enthalpy, so I know what to do there, right? So you'll be able to fill in those blanks.
Mm-hmm.
So you may have to do like 5 of the calculations.
Okay.
Yeah, so it's not too bad, but the real thing I'm after is understanding the problem and what it's calculating. And if you can, you can't really answer the questions about that problem unless you understand it. So I'm not really trying to test how fast you are with the calculator, but can you understand these calculations, of this system? So if you're following me through the notes and these are pretty simple, that's a good thing. When we get to the end, then we'll talk about how to interpret it. And that's why the first question I asked you guys about which side the products is going to be dominant products or reactants is a really key thing. So we're gonna focus on that when we get to the end. So here we've done USHAG for the products. So let's look at the deltas. Okay. Now we're talking about the reaction. So we're not talking about any reactants products. We're talking about the reaction between the two. And so we just take the products minus reactants. You guys should be familiar with that kind of concept, right? You got the energy of the products and you subtract the energy of the reactants and you get your delta. It's always products minus reactants. So 148 minus 88. So it went up 60 wave numbers in this reaction when we go from reactants to products. And the delta H, the delta S, entropy products minus entropy reactants, it also went up. So the right system has more entropy than the left. Can you explain that to me? Why would you look at that and say, oh yeah, that makes sense, or does it? Look at the right system, the products. Why would it have more entropy than the left? More degeneracy, which also just means more options. And we talk about disorder. That's a kind of a weird word because it's hard to define disorder. I like statistical options better. There's more options for the molecule to be in different places on the right than there are on the left. We only have 3 levels non-degenerate on the left. We have 6 possibilities on the right for those molecules. There's more ways to build the product state than there is to build the reactant state. So it makes sense that entropy would go up as we go to the right. Here's the enthalpy. It also went up. And then here's the Helmholtz energy. It went down. Okay. And then so did the Gibbs energy. It went down. So it's negative. Both the Helmholtz and the Gibbs energy are negative. What does that tell us? It's spontaneous in the forward direction. Okay. So, if we started with all reactants, it's going to go forward without any kind of effort on our part. It will work without external input. Okay. And then we need to calculate the equilibrium constant now. Since we have delta G, this is all you need for the equilibrium constant. Now we're going to derive this equation later, but this is the equation for the equilibrium constant. Is equal to e to the minus delta G of reaction over RT. Now, which R are we going to use here, right? We've got energy and wave numbers, so we're going to use the 0.695 so that the units work out. So we have negative 76 wave numbers. We have RT here, so the wave numbers cancel, the Kelvin cancels. So we have a unitless exponent, which is what we want for exponent. Change the sign and raise it, to the e to that power. We get 1.44. So what does that tell us also? The reaction is predominantly in the products. Okay, so this is the answer that we were looking at the beginning, is which side predominates. The products has more molecules in it than the reactants. But the intuition of looking at that system, you should look at that and say, if I'm rolling the dice, let's just think about the dart game, right? There's 6 places for that dart to land on the right and only 3 places for it to land on the left. So just statistically, I'm going to have more molecules on the right. Now, that can change if your ground states are different, right? So if we start raising the ground state at that 0 wave numbers and start moving it up, now Boltzmann distribution may slosh molecules back to the left. So it's not always the degeneracy, it's also the relative ground states. But since these both have the same ground state, then it's just a matter of degeneracy. Does that make sense? Yeah. So Boltzmann's distribution is really the governing distribution for equilibrium. So it'll take into account the different energy levels and their ground states, the degeneracy, all of those things. That's really how we define equilibrium, is using the Boltzmann distribution. Now, you could have also done this equilibrium constant straight from the partition functions. So if you take the product partition function, which was 2.96, and the reactant 1.5, you get 1.44. So like from the very beginning, even above the USHAG deltas, we had the Q's. We had the Q for product, Q for reactant. You could calculate the partition, the equilibrium constant.
Maybe I just noticed that the U and the H match, and the A and G match, is that usually how that goes, or is that
I can't say that it will always match. It probably does, but yeah, I haven't done. We can kind of play around with that in the spreadsheet and see. Yeah, I've not connected them algebraically to like show that they are equivalent. Yeah, so as far as the deltas are concerned. Yeah. Yes. Helmoltz. Yeah, that's it.
What does that tell us about the reaction?
Okay, so that's the spontaneity energy change in a constant volume system. So remember, chemical engineering, if they have the stainless steel reaction vessels, then this will tell them at room temperature this reaction moves in the forward direction in a constant volume situation. It gives energy, has an open system, so it's constant pressure. It's spontaneous and constant pressure. Yeah, and so then you could trying to think where pressure would figure into this. Yeah, I don't know how to pull that thread in terms of
Is it a concept to be equal?
That's kind of what we were talking about. I haven't made the algebraic connection to show that they have to be equal. So it could be coincidental in our simple system. Yeah. Okay, but also some other terms that we're familiar with. Look at the enthalpy. That's how we judge if something's endothermic or not. Enthalpy is the heat of reaction, and heat and therm go together. So it took in heat to move to the right. Okay. And it went up 60 wave number, so it's endothermic. And then what's the term for this? We say spontaneous, and that's true, but there's also an energy term for the negative Gibbs energy and the negative Helmholtz energy. We call it exergonic. Okay. And if it went up, if it was positive, it'd be endergonic. So this term right here, this is about energy, not just heat. And it's this root right here in the middle, erg. Have I gone through the whole MKS, CGS system with you guys? Did I do that in the fall? Does that ring a bell? The joule is the energy for, is the name for energy, joule, in MKS system. So joule is equal to a kilogram meter squared per second squared, right? No problem. Look at what that uses. It uses the meter, it uses the kilogram, and the second. Okay, the erg, and I don't know what the letter is. I just know the name is erg. If there's a letter, I don't know it. Okay, the erg is a gram centimeter squared per second squared. And that's the CGS system. So early on, when they're trying to standardize the SI units, the System International, that's why SI stands for it's in French. There was a camp that wanted to use centimeter, gram, seconds. And so they calculated everything with grams and centimeters as the length and seconds. And that was, and the energy unit was called erg. Okay. But joules won out, like the MKS system won out. And so we ended up with joules and newtons and things like that. So the CGS version of a newton is called a dyne. And you've heard of like dynometers for cars and stuff, the dynes that measure the force on the wheels. Okay. So we see that in places, we see it around. So there's still some language from the CGS system running around in science. And this is one of those examples where when it's spontaneous in the forward direction, it's giving off energy, it's going downhill, we call it exergonic. We also talk about chairs and armrests and tables being ergonomic. That's where that comes from. So ergonomics is a study of how your body energy is maintained by posture, things like that. Okay, so that's a little bit on the CGS and MKS systems. They are not the same number, right? When you do a joule and convert it over to an erg, you've got to get out of kilograms and into grams and all of that. So there's a factor of 1,000 there. There's a factor of 100 squared. Okay, so that's 10,000 going from meters to centimeters. And so they're not the same number, but they're because you've changed the units. Okay. Okay, so now this is a little side trip, so bear with me. This isn't anything I'm really interested in testing you on, but I want to derive and show you where the equilibrium constant comes from, okay? And so let's look at that. Let's take a side trip. When Boltzmann was doing his weighting factor calculations, if you're counting up all the options for, say, putting persons in chairs, you're going to end up with 1 times 2 times 3 times 4. You're going to end up with factorials, okay? And all of these factorials are how you calculate the weighting functions. So when you get to big numbers, the factorials become uncalculable by our machines. Like my old 1987 HP11C would like give an error after 69 factorial. And my phone calculator can get up to 10,000 factorial. So it can go to 2.8 times 10 to the 35,659. Okay. So it's like got what is that, an 8-bit exponent or something like that. But then if I try to go to 10,001 factorial, my phone gives an error. It just can't store the number in its memory. Okay. And what about if you have a mole of molecules? Now all of a sudden you're talking about 10 to the 23 factorial. And my phone or my computer craps out at, 10,000. So to actually calculate, these numbers in your computer or on your calculator or whatever, we couldn't do it for a mole of molecules. Okay. So Stirling's approximation comes in. So there's an approximation to this. So if we have like a mole factorial or some number factorial that we can't calculate, the natural log of that would be this. This is the approximation to the natural log of that. And notice we've gotten rid of the factorials. So that's the reason we would use Stirling's approximation, is to get rid of the factorial. Okay, so let's do it for a mole. We've got Avogadro's number here. We've got the natural log of Avogadro's number, and then we've got minus Avogadro's number. So that's this piece right here. All right, and so then we end up with this natural log is 54.7. Okay, and then we end up with this number, 3.2 times 10 to the 25th. Okay, so that would be the natural log of n factorial. Okay, so if I wanted to get back to n factorial, I raise e to that power. So n factorial is e raised to the power of 3.2 times 10 to the 25th. So the power of e is 10 to the 25th. You can see why your calculator can't calculate that. If we wanted that instead of the base of e, to put it in the base 10, we could divide that number by the log of 10, natural log of 10, and it would be this number. So 10 to the 1.4 times 10 to the 25. So think of how big that number is. It's a 1 with 10 to the 25 zeros. That's how many options you have at rolling the dice with a mole of molecules. It's unbelievable. Yeah. So this is why, it's like every possibility is explored in a mole of molecules. You got molecules 1 at least that is really super excited, and you got 1 at absolute 0, and you got most of them in between. They're trying out everything because just statistically you've got that many chances. Okay. Now this is that weighting factor thing that Boltzmann had on his tombstone. It was the entropy is K log W, and this was the W. And again, it's all chock full of factorials. And so we just really couldn't calculate it without some sort of approximation. Okay, so let's look at the Gibbs energy now. there are just many different forms of these thermodynamic equations. And that's kind of why I was like, I haven't made the algebraic connection between those two, like you were asking, because there are just so many different routes that you can take. But it's a good question. It would take all semester to derive every one, but this is the one derivation I like to do because it shows how the equilibrium constant is rooted in this in these Gibbs equations. So here's one version of the Gibbs equation: is that Helmholtz energy plus PV. Okay, and PV equals nRT, right? Well, nR, R is Avogadro's number times K. So we could break that part out. We could have the number of moles times Avogadro's number times K. And so that what is the number of moles times Avogadro's number? Avogadro's number is per mole. So the per moles cancel and you just have the number of particles. So the number of moles times Avogadro's number is just NK. N is just the number of particles that you have in the system. Okay, so we can make that replacement. So what we've done is we've replaced this piece right here, PV, with NKT. And then this is one of the thermodynamic equations that I was talking about for the Helmholtz energy here. This A is this minus KTQ. Now, we haven't talked about an ensemble yet, because again, it's really not this statistical thermodynamics piece that I'm trying to cram into like 2 weeks is a whole course. Okay, and if we were to take our 2-level system or our 3-level system, and we're calculating the partition function, and we're trying to scale that up to, say, a mole of situations, we would be overcounting because too many of those would be identical. And so we would divide by the number of particles. And so this ensemble is a discussion on how you scale things up. And it would be the small partition function for an individual system raised to the number of particles that have that system. But then to prevent overcounting, we would divide by n factorial. So this is the problem right here, is this n factorial. So this Q piece is this right here. Okay. And it's called the ensemble average. You're not going to need to know that, but that's just sort of tying it into the language of statistical thermodynamics. And we want to get rid of this n factorial. So we need to get it out of the denominator. You know, it's in the log, natural log, and so we could just pull it out and change the sign. We could have a plus KT natural log of n factorial. So that's, you see how it's split apart now? We had minus KT natural log of this ratio, and so now we still just have the minus KT of the top and plus KT of the natural log. Do y'all remember the log properties? Yeah. So. Well, it's already minus, and so we just changed the sign since it's in the denominator. Yeah. So we have this. So now that we have this, we can use Stirling's approximation to get rid of that factorial. So that's why we talked about Stirling's approximation. Okay. So this piece breaks out into n log n minus n. So that's Stirling's approximation. Okay, and so now we can multiply this KT through here, and we have NKT, natural log of n, and we can multiply this NKT over here. Now look at this, we're going to have a minus NKT and a plus NKT, so those guys go away. They cancel out. So all we have left is that first term, NKT natural log of n. And now since we have the same sort of piece out front, we can bring that n underneath this Q, underneath the partition function. So we're back to this fraction. So this n went down here, the NKT came out front, and so we have this. Now we'll go back up here and we'll look at NK is equal to NR essentially. nkt is equal to nRT. So we have this here using the ideal gas law is the same as nRT. So we have these three things. Now something familiar arises out of this, and that is when you have something multiplied by a natural log, you could also move it over to an exponent. So we can take this little number of moles and put it over here. And so our Gibbs energy is the minus RT natural log of the partition function over the number of particles raised to the number of moles. So we have number of moles as an exponent. We've seen that before. We've seen it in the equilibrium constant, right? When you're doing the equilibrium constant, you have the concentration of species A raised to the number of moles of A. So let's look at our reacting system with this equation. So remember A, just pick a reaction, A times, little a times the chemical species, capital A, etc. We have this reacting system. And so let's write this out. This is the products minus reactants. And let's put in these Gibbs equations that we just worked on. So we have the Gibbs energy for C right here. And we have the Gibbs energy for A, etc., and everything. And then the products minus reactants, this is the minus reactants part right here in front of A and B. And so we can also bring those exponents through. We can bring the minus RTs out. So there's 4 minus RTs. So we'll just pull all of those out front. So those are now out front. And then we have the C, natural log of C, natural log of D, those are positive. Natural log of A and B, those are negative because those are the reactants. And we have pluses and minuses in natural log, so we can do a ratio, right? So we can break that in. These negative ones go down in the denominator because they're negative. So the products minus reactants becomes products over reactants when we're dealing with natural logs. Okay. And we have things raised to the exponent. So this looks a lot like our equilibrium constant. And so this is the thermodynamic derivation of the equilibrium constant directly from the Gibbs energy equation. And we see this over time. We learned the equilibrium constant, but we learned it with concentrations, so this is if this piece right here is Kp, the sort of the partial pressure or pressure equilibrium constant, then we have that equation that we just used earlier in the USHAG problem. Delta G is minus RT ln Kp, or switching it around, Kp is E to the minus delta G over RT. So we've used these two equations already, but this was the derivation of them. So let me just talk a little bit about equilibrium and the statistical thermodynamics. So this next slide is kind of the summary of this whole first part of the course. It's kind of this was earth-shattering, and this was really the math that convinced Einstein and others that quantum systems were real. Like quantization wasn't just a trick to explain spectroscopy. Right? We had spectroscopic measurements. You learned that in the fall. You had line spectra of the hydrogen atom. You had the photoelectric effect. You had the black body radiation. Planck used Boltzmann's equation to solve the black body. Was it just a coincidence? Did quantized energy levels really exist? And that was where, when they started doing statistical thermodynamics, Einstein said, I don't believe God plays dice with the universe, meaning that quantized systems are just populated statistically. But when we showed that even equilibrium constants can be explained, then they were, the skeptics were convinced. So that's pretty cool. So the statistical treatment of quantized states can explain the following observations. And in the fall, we had 4 failures of classical physics. We had the line spectrum of hydrogen atom and many other atoms. We had the photoelectric effect, and we had the black body radiation curve. We explained all 3 of those in semester 1. This one explains the heat capacity. That was the fourth failure of classical physics. They couldn't explain how the heat capacity for certain substances like diamond and so on, they were at their equipartition value, and then they dropped below their equipartition value when they got cold. And they're like, what's going on with the heat capacity? Well, it was the quantized effects that were causing that heat capacity to drop below the equipartition. Remember, at equipartition, we have so many molecules in the excited states and so on, they're equally populated. But you start drawing down the temperature, you start seeing the quantum effects. And they didn't know about quantum effects in classical physics. So this explained that the heat capacity was a quantum effect, and that really did solidify people's belief that quantum states exist. Entropy is just a measure of the density of states at a given temperature, the number of states in a given energy range at a given temperature. This is another way to describe the entropy. A spontaneous change, we knew about delta G values, but we didn't know that they were driven statistically, and this explained that. And then the chemical equilibrium constants just depend upon the partition functions of the reactants in the products. So the equilibrium constants you learned in freshman chemistry and used in organic and elsewhere were just approximations. So the concentration is just an approximation of something really difficult to calculate for a liquid, right? Everything we've done so far has just been gas phase or a molecule in a really simple system of 3 levels or something like that. It's really complicated to calculate the partition function of a solute in a solvent, okay? But yet we know that that's an approximation of the partition function. And when our concentration equilibrium constants fail because of activity coefficients, and we have all these corrections, we're still just trying to correct something to get close to the partition function, which would be the true factor in the equilibrium constant. Same with partial pressures. So partial pressure equilibrium constants are just approximations of the partition function. So let's look at, instead of doing a Kahoot, let's look at the spreadsheet version of this so we can play around with temperature. Let's see. Yeah, here we go. We'll try to get the reaction to run in reverse. Okay. Let's see. It's got to download from the cloud. I'm going to go ahead and stop the video and start it again on this one so that you don't have to wait through all the